So our goal is to find the function y such that the integral of some functional of it, some function of y, and possibly its derivatives, and possibly the variable itself, is a maximum or a minimum. So j is the integral, so we're trying to find the y such that j is a maximum or a minimum. We're going to do that by begging the question to some extent. So we're going to break up our function y into the bit that does that correctly. So y naught is the extreme wall function. It's the optimum, and everything else. And if we make everything else arbitrary, then we haven't lost any generality. So alpha is just some parameter, and this is an arbitrary function. Actually has one constraint, which is that we want to start and end at the same place each time. So this extra bit that we add has to be 0 at the ends. At alpha is 0, we've got this y naught, and that's what y is, and that's the best we can do. And what that means, of course, is that the derivative should be really with respect to alpha. At alpha equals 0, the derivative of j is 0. In other words, it's a maximum or a minimum. And we can expand that derivative. It's an integral. The derivative goes straight through the integral because the integral doesn't depend on the bounds. And we've just got the chain rule. So does f depend on alpha? Yes, it does, because y depends on alpha and y dot depend on alpha. So we've got the chain rule, df dy, dy d alpha. And if you remember the multivariable version of the chain rule, if you've got multiple variables, then you have to add up all the different chain rule contributions. So y dot also depends on alpha. And we'd also have a df dx dx d alpha term, except that's 0 because x doesn't depend on alpha. Okay, so this y dot here, remember, it's just the derivative of y with respect to x, so we can expand that out if we like. And assuming that y is sufficiently smooth, it doesn't matter what order we do those derivatives. So I could do a dx d alpha or d alpha dx. So what we'll do is we'll do that second term by integration by parts. So we'll just leave this first term alone for a moment. And we'll do the second term by integration by parts. This second term, you leave one of those alone, but you integrate the other, and we'll integrate with respect to x, obviously, that's our integration variable. And we take away, and we integrate and take the derivative. So we've got a, okay. And then, what do we do? Then we say, hey, I know what this dy d alpha is. If I look back up at my definition of alpha, dy d alpha is just this eta function. So I've got all that times eta. And I've got this extra term, and this extra term is evaluated at the endpoints. And I immediately know that eta is 0 at the endpoints, so I can ignore that term. Okay, so I know that this integral here has to be 0, and it has to be 0 no matter what eta is. So this is true for a completely arbitrary function of eta. And if it's true for a completely arbitrary function of eta, then take a moment to convince yourself that in fact it must be true pointwise. For every single point in x, this thing here must be 0. Because otherwise, if there was one bit of this that wasn't 0, I could just have eta be a little bump over that area, and suddenly I would have this integral not being 0. So what this all implies is that those terms in the square brackets must be identically 0, and that is an equation that the function y has to obey if indeed this integral j is going to be maximized or minimized. And that equation is called the Euler-Lagrange equation.